Welcome back to the last of the 2022 papers even, paper ones for science. This time we're doing physics, which is my personal jam. I love physics, I tutor it, my degree's in it, and it's a lot of fun. So again, I'm going to go through, I'm going to explain everything you need to know, exactly how I approach the problems, and the best ways to revise different things. Sometimes it is just brute force memory, but of course you can hack your own memory to make it better by doing things like targeted flashcards or some other tricks I'm going to show you in a second. So without further ado, let's get into it. So we have here, figure 1 shows a large wind farm off the coast of the UK. The mean power output of the wind farm is 696 megawatts, which is enough power for 580,000 homes. Calculate the mean power needed for one home. Now, the whole mean power thing, or the word mean, you can kind of ignore it in almost all cases when it comes to GCSE science, because even though it does have a meaning, all they're asking you is how much power is needed for one home. Well, what they've done is they've taken these 580,000 homes and they've added up all of their power requirements, and they got 696 megawatts. So in other words, all we need to do is take this number and divide it by the number of homes, because that will be, on average, the amount of power each home uses. So, okay, that doesn't sound too bad. If you notice, the calculation is not worth as much in physics, which is sad, but whatever. The thing we really need to remember is what the whole MW means. So what is a megawatt? Well, if you remember, you do have this kind of order. So your normal watts are just watts, right? But when you go up, you have kilowatts. Now, if you remember, I'm hoping kilo is one that's quite easy to remember, because kilo we use all the time. A kilometer, a kilometer, right? A kilogram, etc. So a kilowatt is the same thing. It means 1,000. So we're going to times by 1, 2, 3. If you want to use standard form instead, that's times 10 to the power of 3. Either one of these is equivalent to each other. Hoping that should be fine. The one above that is a megawatt. That is timesing by 1,000,000. 1, 2, 3. Times 10 to the power of 6. Again, maybe if you know anything about computers, like a megabyte, something like that. The next one you might be asked for is a gigawatt. They don't really ask you for anything beyond that, but that's times 1,000,000,000. 1, 2, 3, 1, 2, 3, 1, 2, 3. That's 9 zeros. If you notice, it's going up by 3 zeros each time, or in terms of powers of 10 to the power of 3, right? So it's 3, 6, 9. There's 3 zeros, 6 zeros, 9 zeros. So again, the next one, which is terawatts, by the way, which you don't really need to know, is times 10 to the 12. So it's 10 with 12 zeros afterwards. Going down, by the way, these are all the same. So K always means 1,000, M always means 1,000,000, G always means 1,000,000,000, a T always means 1,000,000,000,000. It always means that. So if I said instead, how much is a TG, a teragram, it's going to be 10 to the 12 grams. Okay, so they always mean the same thing, and that's the useful bit. But anyways, going down, of course we have things like centi and deci, etc. But realistically, the only one that you're going to need is MW, which is milliwatts, which is 0.001, or times 10 to the minus 3. And then you might be asked about micro. What on earth did that just happen? Okay, micro, which is times 10 to the minus 6. But if you notice again, we're going down in powers of 3. That does mean that the one in the middle is technically 10 to the power of 0. So anyways, long-winded, I know. But since this is megawatts, we're going to 696 times 10 to the 6, because of this, divided by 580,000. What's the best way to kind of learn all these ones on the side? You could write them out like 5 times, and then you'll probably remember them, to be honest. Or just keep doing enough practice questions and you'll kind of get used to it. From there, you just bring it into a calculator, because of course all science exams are calculator. So 696 multiplied by 10 to the power of 6 over 580, 1,200 watts. Okay. Not actually sure if that's accurate or not, but let's just assume it is. Let's assume AQA did their homework. That's all you'd need to do for something like that. So again, main takeaway is A, the word mean. It just means you're going to be dividing the total by however many there are. Don't worry about it. And of course the whole different prefixes that they use for unit scales. With the next one, you do need to know a hell of a lot about renewable energy sources for GCSE physics. You need to know the kind of pros and cons of all of them. However, and I know that that sounds like a lot, but we can also think logically. And I don't mean to say that in a condescending way, but we can kind of use a bit of common sense, a bit of knowledge of the outside world to help us. So on one day, the demand for electricity was 34,000 megawatts. That's 34 gigawatts. So just two reasons why wind power is not able to meet the demand. Well, again, this is the overall power demand of the entire UK. So that might be a good thing to think about. But first of all, well, why is wind power not able to meet it? There's three reasons I come up with. It's only asking for two. One, and this is just one of the downsides to it, is that the wind power is unreliable. And the reason for that is, as you may know just from walking around in your life, wind changes, right? Some days are windier than others. Some times are windier than others too. So the second point, so again, I'm going to do all three. So that's the first one you can say. You could say that day might not have been very windy. Day may not have been very windy. And that's a pretty big one. And the last one, which also hopefully might make sense, is simply put, there might not be enough wind turbines, right? Like, I mean, look at all of these. They don't power the whole of the UK. So maybe there needs to be a lot more. So there could simply have just been not enough wind turbines. And yeah, that's it. But bear in mind, you have to be able to do this for tidal, for geothermal, for literally all of the renewable and even the non-renewable fuel sources, really. You need to be able to kind of say the positives and negatives. I will say that wind and solar are fairly similar. So solar power is unreliable. Why? Because it could have been cloudy. Could have been less sunny. And there's also not enough solar panels. Things like that. Things like the tides, though, that's not really unreliable because the tides are very predictable. They come in and they go out at pretty much the same level every day, bar none, because it's based on the position of the moon and all that fun stuff. Some of the energy from the wind used to rotate a wind turbine is wasted. An engineer oils the mechanical parts of a wind turbine. Explain how oiling would affect the efficiency. So, simply put, again, by the way, 3 marks, 3 points. Okay, so let's put our 3 bullet points right here so we don't go over the limit. Well, what I like to do is actually start. So sometimes in mark schemes they would say efficiency increase or decrease, and then you say why. I prefer to actually kind of do it backwards. So what is the effect of oiling the mechanical parts of a wind turbine? Well, why do we oil something? To reduce friction. Oiling reduces friction. So what does that mean in this context? Well, it means less energy is wasted. Less energy wasted. If you want, you can say as heat, because that's what friction really is. Technically, it's also sound. Like if you open or close your bedroom door, for example, it might squeak a bit. That squeak is wasted energy. It also does heat up the joints. So oiling reduces friction, that's what it does. So what does that mean? Well, remember what efficiency is. Efficiency is useful energy out over the kind of total power output. Let's actually use over the energy out. So you take the useful part out, which in this case would be, I mean, you could call it maybe kinetic energy, or if they're storing it as chemical energy, over the total energy that they've taken in. So that means this fraction gets bigger. So the amount of energy that's useful is bigger. You know what? I'm going to change the word amount to proportion, because we make it a fraction because it's a proportion. So let's say proportion of energy that's useful is bigger. So therefore, what does that mean? If this fraction's bigger, that means the efficiency is bigger. Therefore, it is more efficient. So again, in a mark scheme, they tend to say more efficient because the proportion of energy is bigger, because oiling reduces friction. I prefer to word it from the cause because it helps my brain think. So like, okay, we've oiled these parts. What does that do? Well, we oil things to reduce friction. Cool. What does that mean? Well, there's less energy wasted. Okay, what does that mean? Well, it means the proportion of useful energy is bigger. What does that mean? The efficiency is greater. So keep following that logical chain of reasoning. It's the best way to do it. That's why I don't really like the way the mark schemes go from the kind of the end result to the reason why. I prefer going from the reason why to the end result. But it doesn't technically matter. You can put these in virtually any order. Small little 2 marker here. So in most homes in the UK, there are many different electrical devices. So light bulbs, TVs, computers, charging cables, etc. Explain why people should be encouraged to use energy efficient devices. So once again, you're not really giving your opinion, okay? You're just saying what the effect is. So what would the effect be if we use energy efficient devices? Well, what does efficiency mean? It means there's less energy wasted. So I'm just going to write, they waste less energy. And that is 1 mark on the mark scheme. All I've said is what the definition of energy efficient is. So now, and this is where the second mark comes into play, where it's a bit of interpretation, why should we encourage people to use energy efficient devices? So in short, why do we care about energy waste? Well, what would the effect be if everyone started using energy efficient devices? Well, there's less wasted energy, which means the energy demand is lower. So, or you can say the amount of electricity needed or whatever. Or you could say, minimize the environmental impact, whatever you want to say. But in short, it does minimize the energy demand or lowers energy demand, okay? Anything that means that. So lowers the energy demand, it's more environmentally friendly, less power needed, anything along those lines would all give you the mark in this case. Figure 2 shows a rock found by a student on a beach. To help identify the type of rock, the student took measurements to determine its density. Describe a method the student could use to determine the density of the rock. Here's what I would do. The first thing I would write, very first thing, is density equals mass over volume, which does give you the mark, by the way. But why am I writing it? Well, whenever you have these kinds of experiments, and this works especially if you want to do A-level sciences as well, don't bother memorizing every experiment on the planet. You'll go insane. Instead, think about what do we need? So here, we want to try and determine its density. Well, what do we need for density? We can't measure density directly, but we can measure mass and volume. So we need mass and volume. Cool. Now, how do I measure mass? Well, measure mass using a mass balance, weighing scales, whatever you want to call them. That's your second mark. So again, I'm hoping you can see why this is useful, because what I'm doing is I've really targeted my thinking. Density is mass over volume. How do I work out mass? How do I work out volume? Now, volume is an interesting one because some students might say you just measure the dimensions and times it, but look at the rock. It's a weird shape. So they're trying to get you, and especially because it's 6 marks, trying to get you to say, well, how do you measure the volume of something that is irregular? That's a weird shape. Again, I'm hoping you remember the whole eureka moment thing, where, sit in a bathtub, water falls out of it. But in general, whenever you submerge something in water, the water level rises. And the reason for that is you're adding the volume of whatever the object is. So let's say, that's my excellent drawing, we have water that goes up to, let's just call that 50 milliliters to make it nice. If I put more liquid in, and this should hopefully make sense, if I poured more liquid in, let's say 20 milliliters of water, it should make sense that will now be at 70 milliliters, right? Because I've got 50 milliliters of water, 20 milliliters of oil or whatever it is, it's going to be 70 milliliters. Well, what's interesting is that this happens even when you put a solid object into liquid. Because again, the solid object has volume, it takes up space, and therefore it displaces water, which means it makes the actual water level rise. So now, either way, whether I poured in 20 milliliters of oil or I put in a rock, which is 20 milliliters large, into water, it will do the exact same thing. Again, that's why if you fill up a bath and you sit in it, water flows over the side because you take up space. So, whenever you want to work out the volume of an irregular object, so again like a rock, or in the case of the story, a crown, all you need to do is submerge it in water and calculate the difference in volume. So here's what you need to do. Let's say partially fill a measuring cylinder and record volume. So again, you don't want to fill it all the way to, well, I mean, okay, to be clear, you can fill it all the way to the top, but in my opinion, the easier way to do it is to fill it like, let's say, halfway, read what the volume is, submerge the rock, and it is important that you submerge it, because if you don't, then, for example, if this rock was at the top somewhere, only the volume of the bottom bit is being measured, because that's the only bit that's actually submerged. So keep that in mind. Submerge the... hello, thank you. Submerge the rock and record final volume. So in this case, our initial volume was 50 milliliters. We put the rock in, it's now 70 milliliters. The difference in those volumes is the volume of the rock. The difference in volumes is volume of rock. So if you notice, I've actually done this in 5 bullet points, but then I might want to just say, you know, use mass and volume. I shouldn't put an add sign because that's misleading. I'm going to put an ampersand instead, and volume to calculate density. Again, I haven't done this experiment in quite some time because I haven't taught GCSE physics in a while, at least in school. I've tutored it, but I've still managed to get this answer. Why? Because again, I'm not trying to remember how to do the experiment. I'm thinking, okay, we have mass, we have volume. How do I work out mass? Easy, weigh it. Duh. Volume, well, I can measure the dimensions, but it's a weird shaped rock. So instead, do the only other method of working out volume and submerge it in water. Just to be clear, even if it was a perfect cube and you can measure it, you could still submerge it and work out the volume that way. There's nothing wrong with that. The submerging method works with everything. The measuring method only works if it's a normal geometric shape, like a cylinder or a cube or a sphere or something along those lines. So there's no harm in doing this method for literally any volume. Okie dokie, so the student determined the density of the rock to be 2.55 plus or minus 0.1 grams per cubic centimetre. What's the max and min? This is just bounds from GCSE maths. So what they're saying is the max is going to be add 0.1, so that would be 2.65, and the minimum will be take away 0.1, so that'd be 2.45. That's it. They're literally saying it's 2.55, give or take 0.1. So plus or minus 0.1. So it could be 2.65 or 2.45. That's it. It's just bounds. This table gives the density of 5 different types of rock. You've got basalt, chalk, flint, sandstone, and slate. Which 2 types could be the type of rock? So essentially what we're trying to do here is using this density compared to the densities in the table. So it might even be worth writing the ranges for each of these. So this is 2.8 to 3.0 if I add or minus 0.1. This would be 2.2 to 2.5. This would be 2.5 to 2.7. This would be 2 to 2.4. This would be 2.7 to 3.1. And we can cross off the ones that don't fit in the range. So for example, the maximum is 2.65. So any that start from 2.7, we know it's not. So it's not slate. It's not basalt, because that's 2.8. Okay, cool. So we've got rid of those two. Then we can do the same with the minimum. The minimum is 2.45. So any that are smaller than that, at their biggest, we can get rid of. So we can get rid of sandstone because that only goes up to 2.4, whereas we have 2.45. What 2 are we left with? Chalk and flint, which is indeed one of the answers. That's the way I would do it. But remember, the minimum, you're looking at the maximum value. Because, well, I mean, you can see from the range, right? Like 2.65, well, this is 2.8 to 3, so it's obviously not that. Process of elimination is the best way to do this one. The student only took one set of measurements to determine the density of the rock. Explain why taking the measurements more than once may improve the accuracy of the density value. Well, Again, 2 marks, let's put our 2 points. Why do we repeat measurements? I'm hoping this is something your teacher has hammered into your brain, so it's almost like a gut reaction. But the idea is the mean can be calculated. We want to calculate an average. So, but why do we calculate an average? So that's 1 mark. We've said what we can do with that, but what does that do? It doesn't reduce random errors. Don't say that. It reduces the effect of random errors. Because those random errors will always exist. That's why they're random. You can't get rid of them. So you can reduce their effect by calculating the average, the mean. An engineering company has invented pavement tiles that generate electricity as people walk on them. And it shows these fancy looking tiles. And we need to use the physics equation sheet to answer these 2 questions. So which equation links current, potential difference, and power? Now, they've given you all of these equations. They are on your formula sheet, but what they've done is they've rearranged these formulas. So the equation that you're really looking for is P equals IV. Now, P equals V over I, it can't be rearranged that way, so it's not that. I equals PV, again, you can't actually get I equals PV. This next one's a bit different, but if you look at this one here, V times I is the same as I times V, so it must be that one. It is a bit of rearranging of algebra maybe, but hopefully not too bad. And then it says, when a person walks on a tile, the potential difference of 40 volts is induced across the tile, the power output is 4.4 watts. It's actually pretty reasonable. Calculate the current in the tile. So again, we're using that formula we just highlighted, P equals IV, and we're using it to calculate the current in the tile. Now, some people prefer to use the whole formula triangle thing. So like that. But I personally don't like that. Instead, I prefer to rearrange. So using the formula triangle is obviously one way. I prefer the algebra way, and especially because you have to do GCSE maths anyway, it might be good to practice the algebra way personally. You can sub in the numbers now, so we know that 40 volts is of course the voltage, and 4.4 watts is of course P, so we can now write 4.4 equals I times 40. So then I, you'd divide both sides by 40 and go on there. Again, if you want to use the formula triangle, you would cover up the I, you get P over V, so 4.4 over 40. Whatever way you want to do it is totally fine. I personally recommend the algebra way, especially if you're planning on doing a science or even maths for A level. It's good to get used to doing the rearranging now rather than later. But 0.11 amps. 0.11. Perfect. So we did kind of use the efficiency formula already, but it says what equation links efficiency, total power in and useful out. So the best way to think about it is there's one of 2 ways. Is when you're talking about efficiency, what are you actually trying to measure? You're trying to say how much useful energy is coming out compared to the amount going in. So that means it would be the first one. Another way to think of it is that it always has to be less than 1. So total power in over useful out would have to be more than 1, right? Because let's say you put 100 watts in, the amount of useful stuff out is always going to be less than 100. It's not going to be more than 100, that's for sure. Because somehow you're getting more energy out than you put in. That would like break the universe. And the multiplying, well, again, efficiency needs to be less than 1. If you're timesing 2 things, it's probably going to be more than 1. So that a few different ways of thinking about it. I wouldn't memorize that many equations personally. Instead, I'd think about how they work. But again, flashcards are useful if you're not too sure about it. So we are now going to use that equation we just marked there. It says the tiles are used to power LED lights in the pavement. So I'm guessing this is to replace street lights. An LED light has a total power input of 4 watts. The efficiency is 0.85. Calculate the useful power out. So again, if we look at this, we have efficiency is useful out over total in. So we can write efficiency 0.85 equals power out over 4.0. So all we're doing there, if we wanted to rearrange, is to times both sides by 4, and that's it. So the power out output is 0.85 times 4, which is, so if we double that, that would be 3.4 watts. Let's check. See if I need to hand my degree back to the university. Oh, thank God I don't need to. That's perfect. So 3.4 watts. 3 marks, pretty useful, but again, they don't rely on you having good math skills in science exams, which is why you get quite a few marks for these calculations, whereas in a math exam it'd be a lot lower. So utilize your math skills. That's my number one recommendation, because you get so many extra marks for it. That's a very short equation. You might only get 1 mark in a GCSE maths paper, but in physics we're getting 3. Pretty good. Student investigated the insulating properties of different materials. Figure 4 shows some of the equipment used by the students. So we have this hot water with a thermometer. They've put a lid over the top to stop steam escaping, which would take away energy. They've got a metal can wrapped in some kind of insulation. It could be bubble wrap, it could be cotton wool. I believed I used wool when I was in school. It just says insulating material. Place a fixed volume, put the lid on top, measure time taken for the water to decrease. Repeat steps 1 to 4 using the same thickness of different insulating materials. Identify independent and dependent variables. This again is common between physics, bio and chemistry. So again, I'm going to go through what it is. The dependent variable is what you measure, always. And the independent variable is the one that you're changing, okay? So if you like, the dependent variable is the one that you measure, and the independent is just the other one that's going to change. So the dependent variable in this case, what are we measuring? Where it says measure the time taken. So time taken for T to decrease, right? What is the only other thing changing in this experiment? Well, it says fixed volume, so that's a control variable. It says by a fixed amount, so that's also a control variable. Is there anything else? Nope. But in the last one, it says using the same thickness. So there you go. That's another control variable. But it says of different insulating materials. So our independent variable is the insulating materials, because that's what we're going to be changing. That explains why they didn't actually name what the material was, because they're using different materials. That's what you would do in that case. So again, it is kind of a matter of working through it and kind of using these kind of tricks. I think the dependent variable is probably the easiest one to spot. The control variable is next easiest. Independent can be a bit tricky. It doesn't have to be a numerical thing. The student uses 2 different types of thermometer to measure the temperature changes, and he has an analog one and we have a digital one here. What is the resolution of thermometer B? Well, the resolution of a device is the lowest temperature, the smallest value that you can measure with it. So in this case, what is the smallest number I could measure on this digital thermometer? Well, it goes down to 0.4. So the smallest thing I could measure is 0.1. I can't measure anything smaller. I can't measure 0.01 because look, it's not 2 decimal places, it's 1 decimal place. So the smallest thing I can measure is 1 decimal place. So be really careful when it talks about resolution. You're looking at the smallest thing you could measure with that device. So if you have, for example, a meter ruler, the smallest thing you can measure is a centimeter. With a centimeter ruler, the smallest thing you can measure is a millimeter, and so on. It says thermometer A is more likely to be misread. Give a reason why. Well, there's something called parallax error. Now, parallax error will give you the mark. But what does that mean? Well, the angle, let's call it the viewing angle, affects measurement. That's what parallax error means. A parallax error is an error involved in the use of a piece of equipment. When I use a thermometer, if I look down at the thermometer, I'll read a different value to reading it head on to reading it from below. So that is a parallax error because depending on what level I am in comparison to the actual thermometer, I will get different values. Okay. You can also say something like the number of marks might be miscounted. So right here, for example, there's 1, 2, 3, 4, 5, 6, 7. People might have read that as 8 instead. You know, those kinds of things. For one type of insulating material, the temperature decreased from 85 to 65 degrees. The energy transfer is 10.5 kilojoules, and the specific heat capacity is this. Calculate the mass of water in the can. So you're looking at E is equal to mc delta theta. You might also use depending on an exam board and things like that, delta T. But basically this thing here just means the change in temperature. Now in this case, I know before I subbed in the numbers and then rearranged. I actually prefer to rearrange first because it's a bit more complicated when you sub this in. So I'm rearranging for mass. So as I can see, all I'd do is I'd move everything over to the left hand side as a divide. C delta theta is equal to mass. So then mass is equal to energy, which is 10.5 kilojoules. Remember what kilo means. It's times 10 to the power of 3. Or you can just write 10,500. C is 4,200. Delta theta. Now the change in temperature is a really interesting one because obviously you don't want to do 65 minus 85. That gives you a negative. So all you're looking for is the actual difference between the numbers, which is 20. Or you can write 85 minus 65. Again, any of these is totally fine. The reason why you get a negative is because the energy is taken in versus given out, for example. But yeah, don't worry about that. So 10,500 is the same as 10.5 times 10 to the 3 over 4,200 multiplied by 20 gives me an eighth. So we have 0.125 kilograms of water, which does make sense. We're not going to have that much water in the can. 0.125 is pretty reasonable, 125 grams of it. Last question for this, we have the results for two insulating materials, X and Y, and we can clearly see X has a much shorter time to decrease by 20 degrees than Y. Explain how the results in table 2 can be used to compare the thermal conductivity. So thermal conductivity is how good of a conductor of heat a material is. And if you think about it, the bigger the thermal conductivity, the quicker it will change temperature, because it's conducting heat and giving off heat far quicker. So how can we use the results? Well, what we can do is, depending on how you want to write this really, but the way I'll probably write this is, because it's the same temperature difference, same T difference, but in a shorter time, means X has a higher thermal conductivity. I mean, yeah, you don't really need to write means that X has. You can just say it means it has a higher thermal conductivity, as I just said. Thermal conductivity, because the rate of energy transfer is higher. That's probably what I would write in order to get the marks in that question. So I'm going to maybe tell you a bit of a hack for this question and for a lot of questions like it. So a student rubbed a plastic rod with a cloth. The rod became negatively charged and the cloth became positively charged. Explain why the cloth became positively charged. Now, when something becomes positive or negatively charged, it is only due to one thing. For something to become positively charged, and this is true always, it has to lose electrons. And for it to become negatively charged, it has to gain electrons. That is true always. So, when it says explain why the cloth became positively charged, you can write, if you'd like, that the cloth lost electrons, or electrons were transferred from the cloth. 1 mark. Because that is the only way for something to become positively charged. Now, where'd you get the next mark for? Well, it'd be good to say where they went to, and then why they moved in the first place. So, how did it become positive? It lost electrons. Where did those electrons go? Why did they get removed in the first place? That's your 3 marks. So, transfer from the cloth to the plastic rod. How do I know it went to the plastic rod and it didn't just fly off into the atmosphere? Because it tells me the rod's negatively charged, so it must have gained electrons. If the rod didn't become negatively charged, then you'd just say the electrons flew off into the atmosphere somewhere. They just went away. So why? Because friction between the cloth and rod transferred the electrons. That's it. So the reason why it's a bit of a hack is because any time something becomes positive or negative, it is because of the movement of electrons, always guaranteed. Figure 6 shows the negatively charged rod on a balance. So we have this negatively charged rod, an insulating material, which is, well, it's the weight, isn't it? Now there's another charged rod being held above the rod on the balance, and as you can see, the weight, or the mass that's being read, has gone up. Interesting. Explain why. Again, 3 marks. Well, it would be good to know how exactly this mass balance actually works. It works. It doesn't actually measure mass, it measures weight, which is why we call it a weighing scale. Because what it does is weight means things are pushing down on the balance, which increases the value. How do I know this? Well, if you next time you do an experiment, try not to get caught because you might get a detention, but the next time you're doing an experiment, just push down on the weighing scale with your hand. And it gives you a weight, right? So it obviously isn't measuring the mass of your hand, because I could put my hand on it and it measure, let's say, 5 kilos. I could then push down and measure 10, 15, 20 kilos. So it's not measuring the mass of my hand, it's measuring the force of my hand on the balance. So that's the really key thing here. These weighing scales measure force, not mass. It's just that what it does is it takes the downward force and it divides it by 9.81 or 10 or whatever value you use for gravity to turn it into a mass. So, in short, the only way for this reading to increase is because this charged plastic rod must be pushing down on this other rod. So, there must be an additional downwards force on the balance. How do I know this? Because the mass has increased. The only way for the mass to increase is if there is a downwards force, an extra downwards force acting on this balance. Now, where did you get the 2 marks from here? Because you have to explain it. Why? These two things aren't touching. Well, first of all, does it make sense, logically, that the downwards force, the additional downwards force, must come from this other plastic rod, right? Because that's the only difference between this scenario and this one, is that this one here has a charged plastic rod. Okay, so we know that this rod is somehow causing an additional downwards force. Now, what could it be? Well, what is the other piece of information they gave us? Well, it's negatively charged here. Okay. Therefore, this charged plastic rod must also be negatively charged. Why? Because like charges repel. If I put 2 negative charges next to each other, they're both going to push away from one another. There's an additional downwards force, therefore the mass has increased. Or it looks like the mass has increased. So, because the held rod is negatively charged, and like charges repel. That is the only way that the mass reading on this weighing scale, this mass balance, has increased, is because there must be another downwards force. Where does it come from? Well, they're both charged rods. They must be the same charge because they're repelling each other. That is the only way for that to have happened. The balance had a 0 error. The 0 error is not important in this experiment. Give the reason why. So, 0 error means that if I were to take both of these rods off of the balance, the reading would not be 0. Instead, it might be negative something, might be positive something. It's just going to be a number, okay? So why do I not care? Well, let's say the 0 error means that we've actually added 0.1 grams. Yeah, let's just say that. That means on this one, there's also an increase of 0.1 grams. Because we're looking at the difference in the masses, it doesn't actually matter, right? Because when I subtract them, I'm going to take this extra 0.1 and subtract it from this 0.1. Okay, what if it was a negative? Well, again, the same thing's going to happen. Let's say it's actually 0.1 lower. Well, again, when I take the difference, it's going to, like, if I take the difference between 1.4 and 1.5 versus adding on an additional 0.05, the difference in these numbers is the same because the same number's been added or subtracted from both values. so it doesn't make a difference. So the reason why it doesn't make a difference is because only the change in mass is, let's say, observed, right? That's what we did in this case. So hopefully that makes a bit more sense. A negatively charged rod is held near an earth conductor. Explain why a spark jumps between the negatively charged rod and the earth conductor. So this actually is how lightning forms, because of the large potential difference between the clouds and the earth. So that causes the movement of electrons. So simply put, there is a large potential difference, PD, between objects. And again, this works with the clouds and the ground, which causes negative, actually I'm not going to write negative electrons to travel from rod to conductor through the air. So it looks like a spark to us, or it looks like a lightning strike, for example. And again, that's exactly how lightning strikes work. So here we have the national grid. It always comes up on paper one. It's a really, really important part of the spec that they like to put on. And it says, figure 8 shows how electricity is supplied to consumers from the national grid. So power station, transformer X. Then we have the transmission cables, which you might see alongside motorways, for example. Transformer Y, and then straight to our houses. So why the hell do we even need transformer X? Well, let me go through it. And again, it's a 4 marker, so we're looking at 4 bullet points. So transformer X is something called a step up transformer. Transformer Y is a step down transformer. But you might not be sure as to why we need to step up or step down, or what we're stepping up or stepping down. When we step up with the transformer, we increase the potential difference and therefore decrease the current. Because don't forget, if we increase voltage, it will decrease the current because the power will be constant, P equals IV. The reason for that is when we have a current, we heat up wires, which means we waste energy. So because these overhead transmission cables go on for kilometers and kilometers and kilometers all across the country, we want to waste as little energy as humanly possible. So the way we do that is by making the voltage incredibly high and therefore the current being very low. I'm not sure if you've ever seen those videos of really stupid people trying to touch those cables with like a metal rod or whatever, and it's like a really loud electric lightning strike that goes off. It's because it's a huge voltage that goes through them. So then why do we need to step it down? Well, the thing is, if we put that level of voltage through, let's say, an oven, a microwave, your phone, a computer, or a TV, it would blow up. So what we have to do is lower the voltage again and increase the current to prevent all of our stuff blowing up, simply put. So why is transformer X used? So transformer X increases potential difference, that's 1 mark, and decreases current, 2 marks. Why do we do that? Remember, it reduces energy lost due to heating the wires. And what is the overall effect of that? Why do we care about energy lost? It increases the efficiency. That's the key thing. And then that's it, 4 marks. That's the whole reason why we use those transformers. And then I probably should have seen this coming. Part 2 is why is transformer Y used in the national grid? Well, it lowers the potential difference. You can write and increases current if you'd like. And why is that? What was the reason I mentioned? It's because all of our stuff would blow up otherwise. So we can say that it lowers let's just say to a safe value. How about that? Because that's the whole point. It's about safety. If you have a really large potential difference, you risk, well, like I said, blowing stuff up, which you generally don't want to do in a house. This is a 4-mark question, and we get given the energy, so let's label that as E, and we get a voltage, and we want to calculate the charge, so Q. Now, generally speaking, voltage is equal to the energy per unit charge. So if we rearrange that, we want to work out Q, so we can basically swap these two around. We get Q is equal to E over V. That will give us our 4 marks once we've actually worked it out, which is really nice. So again, calculations are our best friend here, which, give me the calculator please. 3.24 multiplied by 10 to the power of 11 over 230 gives us a really big number that I'm going to have to use standard form. It says the 3 significant figures, so we can actually do this. We can actually write 1, 4, 1, and then how many zeros would that be? 1, 2, 3, 4, 5, 6, 7. Jesus. 1, 2, 3, 4, 5, 6, 7 coulombs. If you want, you can write that in standard form, which would be 1.41 times 10 to the 9 coulombs. Both of those would give you, they both give you the right answer. This is my personal favourite topic in physics, which is the whole radioactivity stuff. And it does come back in A-level physics if any of you are interested. But we have alpha particles, beta particles, and gamma rays are types of nuclear radiation. Gamma rays are photons, high energy photons, so light. Beta particles are electrons. Alpha particles are helium nuclei. So if you'd like, you can say either a helium nucleus, or you can say 2 protons and 2 neutrons if you'd like. Either one's completely fine. By the way, you have to write out protons and neutrons. You can't just write P and N, just so you're aware. Next, krypton nucleus decays into rubidium by emitting a beta particle. Complete the nuclear equation for this decay by writing the missing number in each box. All you really need to know, and this is something that's quite important, is that the numbers on both sides need to match. So what do I mean? Well, 85 plus 0 has to equal whatever it is on the other side, which is 85. So the mass numbers are conserved. So if it's 85 here, all of the mass numbers on the right side have to add up to 85. And the same thing is true on this. So here we have 36, and this is something plus minus 1. So something minus 1 equals 36. That must be 37. That's it. It's literally a game of like filling in the blanks like you did in primary school, right? So 36 is equal to something minus 1, well, 37. 85 is equal to, something is equal to 85 plus 0, that's 85. Now we get a 5 marker. Lovely. Internal contamination of the human body means radioactive material is inside the human body. Explain how the risk from internal contamination is different to the risk from external by a source of alpha radiation. So, this is all to do with the kind of penetrating power of alpha radiation. Alpha radiation is absorbed by a few millimeters of air. So realistically, if it's outside your body, it's going to hit your skin at the most, and it will only damage the surface of your skin. Now, if you don't know, you shed skin every day. And the reason for that is the surface of your skin is actually usually dead, which is its intention. That means anything that lands on your outside skin will be shedded off and it'll be fine. Problem is when it's inside your body, it's going to hit internal organs, which aren't meant to be damaged, which is really bad. The other problem is alpha radiation is incredibly ionizing, which means it damages DNA. Again, the surface of your skin being damaged, that's not really that bad. In fact, that's what a sunburn is. A sunburn is when your skin starts committing suicide in order to shed off mutated cells. So the sun will ionize your DNA and it will cause cancer of the skin. Most of the time, your body will then shed the skin in order to protect itself. Or if you have lots of melanin, that will also work as well. The problem is when it's inside the body, your body doesn't have that kind of defense mechanism inside of it. So if it hits your stomach lining, for example, it can cause stomach cancer, as an example. So, alpha radiation has low penetrating power and therefore is stopped by the skin, which is completely fine. So if you want, you can write it's low risk. You don't have to, but I want that for your understanding more of anything. However, internally, or let's say inside the body, alpha radiation is absorbed by, it could be organs or living tissue. So again, remember what I said, your skin is normally dead on the outside intentionally by design. So, This has a increased risk to damaging DNA or causing cancer because alpha radiation is highly ionizing. So what are the key things here? Well, obviously you need to say the low penetrating power and the highly ionizing because that's specific to alpha radiation. And this question does specify alpha radiation. Other than that, you just need to think about why it's... I mean, I'm not going to say good versus bad because obviously getting irradiated is bad anyway, unless you want to turn into the Hulk. But you need to kind of think about why is it worse on the inside of the body than outside? And it's simply because the skin is a defense barrier. If it's outside, it's not too bad. Inside, it's going to be absorbed by your heart, your lungs, your stomach, which is really bad. So that brings us to the next topic, which is the specific latent heat of vaporization of water. So essentially, you heat up water, and heat it to a boil, keep it boiling, and measure the mass of water left after 600 seconds. So which measuring instrument would you use to measure the volume? Well, normally you would use a measuring cylinder or a measuring flask or a burette or anything like a measuring beaker. That would also work. But any of those, so I'm just going to put measuring cylinder because it's the one that I just thought of first. But measuring beaker's fine, or anything you normally use to measure volume is okay. What is a hazard in the student's investigation? Burns, boiling water, heat-proof gloves, or safety goggles? But it's obviously not these two because they're not a hazard. A hazard is something that can cause danger to you. Now, in terms of burns, not really. Although I do get why people would say burns because the heater's there, but realistically, you're not going to touch the heater. So it's more the fact that it's boiling water that's the hazard. Although, to be honest, yeah, burns is a bit of an awkward one. Boiling water, though, is a bit more obvious to me. And here we have the calculation, a 5-marker, a big fat one. So the initial mass of the beaker in the water was 0.8 kilos. It then drops to 0.071. So that is a difference of 0.009 kilograms. That's about 90 grams. Yep. The energy transferred was 25,200 joules. We need to work out the specific latent heat of vaporization. Well, latent heat of vaporization is E is equal to the mass, the change in mass, times the latent heat of vaporization. So all we need to do is divide it over. We have E over M, which is 25,200 over 0.009. And that will give us, opening up the calculator, the latent heat of vaporization is meant to be a fairly big number, by the way, so don't be put off by the fact that it is quite large. I can tell just because, yep, so 2.8 times 10 to the 9. So either you can write 2,800,000 or 2.8 times 10 to the 6 if you'd like. It does say to give the unit. So what is the unit? It is in joules per kilogram. How can you work that out if you're unsure? Well, on top here we have joules and we're dividing by kilograms, which means our units will be joules divided by kilograms. That's probably the best way to put it. The unit does give you a mark. Some thermal energy was transferred to the surroundings while the water was being heated. How would this affect your value? Well, that means not all of this energy actually went to heating up the water. So the energy that was used to boil the water is actually less than this, which means our value is too low because it hasn't actually been used for that. So, too high. I don't know why I said that. So less energy was actually transferred to the water. So again, ignore my little brain fart there. Again, not all of this energy went to the water. Some of it was lost to the surroundings. That's what it's saying here, which means our actual value of energy should be lower, which means our value is too high. Thus, students' value too high. Too high. Some of the water evaporated before its temperature reached 100 degrees. How would that affect it? Well, since we only really care about the mass that was actually at boiling point, that means the difference in mass is too high because some of the water evaporated before its temperature actually reached boiling point. This can be due to a variety of things, by the way, but essentially we only wanted the mass that was boiled away at 100 degrees Celsius. So change of mass is too high. Mass is on the bottom here, so that number would be lower. It's lower than it should be. So, by that I mean it should be a lower number. Since we're dividing by a bigger number, that means our answer was too small. Hence, students' value too low. Again, that's because this number right here is bigger than it should be because we're dividing. That means the number is too big. And here we have a girl trying to do an experiment to show, to determine her power output by running to the top of some stairs. So essentially what she's going to do here is she's going to convert kinetic energy in terms of the running into gravitational potential energy, because whenever you go up a height, however you may do it, whether you jump, you go upstairs, you go up in an elevator, you are transferring energy into gravitational potential energy. That change in energy, that energy that she gains, she's going to divide that by how long it took her. Because remember, power is equal to energy over time. So if our energy is equal to mgh, we're just going to do mgh divided by time. In fact, that's literally all we have to do, 5 marks. So energy is equal to mgh. You could do this all in one step, but let's just leave it as this for now. So that's 60 kilos times 9.8 times the height of the stairs, 175 centimeters. That's really short. Most people are taller than that. Anyways, we want that in meters, don't forget. So you don't want to use standard units. So you want kilograms, you want meters, you want things like that. So 60 times 9.8 times 1.5. She used 1029 joules of energy. Now again, power is energy over time. The way you know this as well, if it helps, you can go through and label what each of these things are. Each of these units are. If that helps you. Some people don't need it, some people do. It is a complete matter of preference. Over 1.4 seconds. It's pretty quick. So divide by 1.4, that would give you her power output, 735 watts. 5 marks, pretty good, but again it's because we had to do 2 separate calculations, that's why it's so much. Interesting. The total power output was actually greater than the answer here. But why? Well, think about it. I said if you move up, right, if you increase your height somehow, you're going to increase your gravitational potential energy. But that's not the only form of energy she's using. She's also using, well, first of all, kinetic energy, but also thermal energy. What happens if you run up a flight of stairs? You get a bit hot and sweaty. That's thermal energy. But also you need to move to do it, right? Like you don't just stand at the bottom of the stairs and you teleport to the top. You have to move in order to do that. So some of her energy is actually not gravitational potential, it's also kinetic and thermal. So that's the 2 different reasons why. So girl increased her kinetic energy as well as gravitational potential energy. And for number 2, I'm going to say some energy is wasted as heat to surroundings. Again, whenever you get hot and sweaty, that's just wasting energy. Wasting energy as heat to the surroundings. So, a boy took more than 1.4 seconds to run up the same stairs. So remember, she took 1.4 seconds. He's taken more than 1.4 seconds. The power output was the same though. So what conclusion can be made about the boy's mass? Interesting. So despite the fact that this number here, this bottom number is bigger, his output was the same. So that's interesting. The only way for that to happen is this number got bigger, it means the energy also got bigger. Well, what does energy depend on? Well, it depends on the mass, the gravitational strength, field strength, and the height. Now, because it's the same flight of stairs, the height was the same. so that can't be what got bigger. Because he's also on the same planet as her, G didn't change. So the only thing you can say is that his mass must be bigger because his energy must be bigger because this thing was the same despite the fact that the denominator got bigger. So it says the boy's mass must have been greater than the girl's mass. That's the conclusion that you can draw. And hopefully that makes sense. If not, again, please let me know in the comments and I'll explain it further. If you ever look at the mark scheme for this whole of question 10, it was actually discounted in 2022 because the advanced information said this wouldn't come up, and it did. So everyone was given 100%, which means the exam... I like to use the examiner's reports to help me understand where students are going wrong, because it tells you. You can't really use it for question 10 because, again, students were told not to study it and then it came up, so they completely erased the question after the fact. So just be aware, if you use examiner reports, question 10 for 2022, physics, obviously, this was discounted, so you can't use that information because it's not accurate. So, launching toy aeroplane, and it gives you an extension. So normally I give extension as the letter X. We get the mass, of course, spring constant K. Calculate the maximum speed. Interesting. Well, whenever you do this kind of thing, the elastic potential energy is going to be transferred. So this is elastic potential energy, EPE. Once you've released the toy plane, that's my perfect plane, it's all now turned into kinetic energy. So all we need to do is work out the total EPE and then make that equal to the kinetic energy. So how do you work out elastic potential energy? It's a half, as most things are, times by the spring constant, times by the extension squared. Again, this was on your formula sheet, but either way, kx squared, okay? Work out what that is. You can do this all in one step, by the way, by just equating the two equations straight away, but I'm going to assume most people don't know how to do that, so that's why I'm doing it by hand. Just so you know, 0.36 joules of energy. Whopping. That is now our kinetic energy, which is half mv squared. So we have 0.36 equals a half. The mass was 0.02 times v squared. So if I times both sides by 2, I get 0.72 equals 0.02 v squared, which means v is equal to 0.72 over 0.02, because I've divided both sides by 0.02, and then I square root it, and I'm done. In terms of the unit, that's of course meters per second. So I've times it by 2, divide by 0.02, then square root our answer, we get 6 meters per second. Nice. Complete the sentence. As the aeroplane moves upwards through the air, there is a decrease in the blank energy of the aeroplane, where as it moves upwards, this EPE is going down. However, it's talking about after it's in the air, so my apologies. Well, as it goes through the air, it's going to start slowing down, isn't it? So that means the kinetic energy will decrease. Give one factor, which would increase the distance the toy aeroplane travels horizontally. Interesting. Well, that means you'd have to give more elastic potential energy. So you can either, more elastic potential energy works. More EPE. You can also say how you would do that in order to get the mark. So more spring constant K, more extension also works. You can also say lowering the angle, so making it more horizontal as well. And that is it for question 10. Nice and quick. We're doing some circuit stuff. Electric circuits or electricity is often the tricky topic in physics for sure. But LED, just draw the circuit symbol. It is a line. Then you're going to have a triangle, which represents a diode. Don't forget technically this is the diode symbol. And then all you're going to do is draw light coming out of it. That is your circuit diagram. Okay. Here we have the circuit diagram for the hair straighteners. Fascinating. Each resistor is a heating element. The power output can be changed by closing different switches. Cool. Those of you that don't have, I mean, I use hair straighteners all the time, as you can see. So for those of you that want to like use your parents or something, you might be able to see that you have different settings. This is how it's done, by adding more heating elements, by closing more switches. So when you turn it on, just S1 is closed. You can make it hotter by closing S2 as well. Close it hotter again. So why do the hair straighteners not turn on when only S2 is closed? Well, if I only close this, it's not a complete circuit. So there is a gap in the circuit. Gap in circuit. That's all I would write. Because yeah, it's not a closed circuit. Hair straighteners have a maximum power output of 120 watts. The energy transferred to reach normal operating temperature is 3.6 kilojoules. Calculate the time taken. Okay, so this is one of those questions where it's just power is energy over time. So to work out how long, you just swap those two numbers around. We have power, time is equal to energy over power. So that is 3.6 kilojoules, so that's 3,600 normal joules. Remember, keep the units consistent. Over 120, that would be 30 seconds. Cool. Nice and easy. And the very last question is an electricity question. Of course it is. So, these hair straighteners are in the circuit. So they close S1. Then what's going to happen is they close S2 and then 3 at the same time. Explain what happens to the power output of the power supply. Well, the first thing you should note is that the actual resistance in the circuit decreases because these are all connected in parallel. And remember, in parallel, resistances actually decrease because they add as 1 over the resistance. So, overall, the total resistance of the circuit decreases. And that's because resistances in parallel actually become smaller. So what does that mean? Well, if you have V equals IR, right? As you can imagine, so V equals IR. This is staying the same because the power supply for the UK is the same always. But we've decreased resistance, but that means the current has to increase. As soon as I work out, there we go. Thus, the current must increase. And if you remember P equals IV, power must also increase. So again, voltage is constant, but because we've decreased resistance, current has to increase. That means because of, again, P equals IV, we've increased this and this has stayed the same. Power must also increase. And that brings us to the end of this one. Do let me know if you want me to do some more questions or, more papers, or if you want me just to find the really hard questions, or you want me to do topic overviews or whatever. But other than that, I'll leave you to it. Have a great day.